Hello and good afternoon. Today we will talk about linear regression, another very important topic in statistical analysis or in statistical learning. And the linear regression, by linear regression, we discussed briefly about linear regression, if you remember, when we were when I was in Rwanda. The idea of linear regression is when we wanted to compare relationship between variables, how strong the relationship is, anyone what kind of relationship they actually follow. These type of questions we can ask very easily through a linear regression or a variant of those regressions. But before I continue with the topic, let me appreciate your effort in both of the lab reports one and two both. I'm really impressed with your performance so far. uh, I noticed that you have been working hard trying to get the concept. I know that statistical topics which we discussed earlier and also some through video lectures are not that easy to grasp. But I must say that you have been working really good. You spent some time to understand the idea and somehow you managed to utilize those methods or somehow use them practically through SPSS. However, I do have few suggestions in order to improve those reports in future. So there are a couple of points which you should remember actually. Like do as much as you can to explore the method, any method. I'm just mentioning here hypothesis testing, ANOVA, but regression, principal component, whatever, which which will be learning in this whole course in future. And you learn its usability in understanding the data. So you need to learn the topic, the idea of the method, what the method tells, and when we can use that method. This you need to be clear about. Once you have a data, you can apply that method to the data to understand the overall picture. When you write your conclusion, I noticed that you emphasized more about p-values and rejection and not rejection of hypothesis. This is okay, of course. This is very useful, but it is technical. So I suggest you to use them, and but right after making your conclusion, because this is just a criteria to conclude. Right after that, switch to explaining the conclusion in a layman language. Because as I said, when you leave the university, nobody knows about p-value or hypothesis or rejection or not rejection. So you have to explain a general people about your results, your findings. So I notice that you can do that, but you just need to think a bit about, and then when you write, stress on that particular issue. Materials which I usually give you in labs are very elegant and very detailed. I can understand that, but I'm pretty sure they are very useful to you. So read them aloud as many times as you want and learn the way the analysis and the conclusions are formulated in my labs, because they will help you a lot to construct your own problem in your project, and your project will be graded based on your performance. So in order to have a good performance, or in order to, I mean, somehow perform better in your final project, you should consider those assignments very carefully. You should read them, you should understand them, the structure. As much as you understand, it's very likely that you will be getting good grades in your final project. Yeah, again, the same point. Remember that your client is not familiar with statistical terminologies, to use some type of journal understanding about the results and explain them, write them in your report. Here is a brief guideline for the final project. We discussed this previously as well, but here is some kind of structure, a kind of repetition. Just read those points, just go through this slide, this page, and try to understand the whole structure. I don't think it's too difficult to follow. It's very straightforward, and most of you might have been familiar with these structures. So let's come back to the topic, regression. So we'll talk about the general framework of regression and some terminologies which we will be somehow recalling them in future as well. So a regression model is a model of relationships between some covariates and an outcome. So now this is important. When I say covariates, it means variables which are correlated. Or if not in that way, you can think like variates that are, or variables that are actually influencing the outcome. Outcome is the one, sometimes we use the word response for the outcome. For instance, you wanted to know how much, you wanted to know the grades of your grades attained by students in this course. So this is your response. And this response can be depending on many factors, like how much time students spent on practicing the problems in this course, and their previous backgrounds in education, for instance. So these are the variables, they are called covariates, and the outcome is the grade, which is the response. So specifically, regression is a model of the average outcome given the covariates. So we have a set of variables, we call them covariates, and we wanted to know their effect or their influence on the outcome or on the response. So generally, we use a letter of capital Y to describe the response. So Y is a response variable, which is always dependent because it depends on many other variables. It depends on many other covariates, many factors. And that's why we use the word covariate, because Y depends on those variables. X, we use a notation for covariates or explanatory variables, sometimes we call them. They, most of the time, they are independent. But sometimes they are not independent. So there are ways to tackle this issue if they are not independent. But we somehow assume that they are independent. Like the time you spent on learning about this course and your previous education, they should be independent, right? Mathematically, we can formulate a regression equation in this way, where y is equal to function of x, like function of x means how those variables, those x, influence y. What is the mathematical structure of this influence, right? So that's how we use we write any model, any mathematical model, or any regression, so to say. And there is some error attached to it because we know that there is always a chance of error, measurement error or sampling error. So here f represents the systematic information that x provides about y. Again, the same statement in a more structured way. So main challenge is to identify this function. So main challenge is to find how those two guys, y and x, are related to one another. So we call this dependence a linear when there is a linear relationship between x and y. Remember the line equation we talked about when I was in Rwanda? We did some maths on the board, and then I told you that this equation is linear because the maximum power of variable in this equation is actually 1, right? And those guys, alpha and beta, are the vectors or the constants actually associated with this equation. So alpha is a vector and beta is a matrix, and I call beta is a matrix because x can have many variables, right? If x has two variables, then beta is a matrix. If x is only one, then beta is a one value. And you will see soon how these things uh, can be observed from the data or from a practical problem. So we call us, there are some terminologies which you should remember about. You should keep this in mind as well, like simple linear model. Simple, when we use the word simple, it means if x and y are one dimensional. One dimensional means only one vector or only one variable. When y is 1 and x is 1, we call them a simple linear model. But if there are many variables, many x variables attached to a regression, we call them a multiple linear regression, right? It is linear, but it is called multiple because now we have multiple number of variables attached to this regression. And similarly, this regression can be called multivariate if there are many response variables as well. So in the last part, you have lots of response variables and lots of X variables, and that's why we call them multivariate. By multiple, we only mean lots of X variables, only one Y, but lots of X variables. Regression analysis is useful for fitting a two set of data and to see how data behaves, how correlated they are actually, what is the relationship between those variables. That's what we call them fitting. And prediction means if we know their relationship, we can predict future. Keeping their same relationship in mind, we can somehow assess what will be the value in future, value of X or value of Y. Calibration is the same phenomena, somehow like fitting. Budgeting and cost control is also, if we know how things are moving, we can control our budgets for a problem or for from a business point of view. So let's have an example, linear regression on real data. Now suppose that an statistical consultant is hired, like you guys are hired by a client to provide advice on how to improve sales of a particular product. A client has hired you to get an advice on how he or she can improve sales of a particular product, right? So the data set consists of sales, which is a response because that's what he is interested in. He wanted to improve the sale. So sale is a response variable, and since it's a response variable, then it is a dependent variable as well, right? Of the product in 200 different markets. Advertising budgets like predictors or independent variables or covariates, there are many names about these guys. And I mentioned here all, well, I know that it's a bit complex, confusing, but the reason why I mentioned them here is that when you open a book or a node, you do not get confused. You should be familiar with this idea. So predictor, covariates, independent variables. Three names for one guy, which is X. Response or dependent variable, two names for one guy, which is Y. So advertising budgets from three different media, TV, radio, and newspaper. So there are three um, media partners, so to say, where the advertisement budget has been used: TV, radio, and newspaper. And the idea is to assess sale, see how much sale, how can we improve the sale, right? So now here are some scatter plot between those media partners, media groups, and also the sale. We can see that TV and sale somehow is increasing. There's a linear trend one can see, right? Initially it was not that high, but start moving up in an increasing order. The more you spend on TV advertisement, the more sale you are getting. That's what we can see from this simple, beautiful plot. Similarly, relationship between radio and sales, we see that, yeah, not very obvious, because even though I'm spending too much on radio here, 40, sorry, yeah, 40, whatever the unit is, we don't need to concern about that. But sale is still not that high. But all of a sudden, sale goes high as well. So yes, it says that radio do improve the sale, but it's not clear what is the relationship between radio and sales. Like here, it was linear, but here it's really hard to see. Similarly, for newspaper and sales, again, the relationship is not very obvious. It's strange. We see that in the beginning, when newspaper was, then there was not much spending on newspaper advertisement, even though the sale was really high, right? And if I spend too much, then sale is not that high, like here, this dot, this circle. So somehow it's not either clear here as well, like how newspapers advertisement and sales are associated with one another. So far from these three pictures, I can see that TV is very linearly associated with sales, but I am not sure about radio and newspaper. Yes, for radio, I can see some type of relationship, but not very obvious. For newspaper, there is no relationship I can see. So few questions we might ask to address to explore the pattern hidden in the data. Like, is there a relationship between advertising budget and sales? And if so, how strong is the relationship between advertising budget and sales? Which media contribute to sales most? How accurately can we predict future sales? Is the relationship linear? Is there synergy among the advertising media? I mean, are they connecting with one another? Are they depending on one another? So these are a couple of questions we can formulate. So, and these questions can be answered very simply through linear regression by just running a linear regression, and we can answer them immediately. So like here mathematically, this is a simple linear regression, and where alpha is the intercept and beta is the, well, we use the word slope for beta because beta tells us how tilted this regression line is, the trend line is. So together they are called the parameters or coefficients. In our previous example, suppose X represents TV advertisement and Y represents sales. So we can regress sales onto TV by fitting this model. So like here you have sales equal to alpha plus beta times TV plus epsilon. So in this equation you have only one predictor, which is TV, and one response, which is sales, and that's why we call them simple linear regression. So we run regression on those two data sets, and then we evaluate the values. So the regression fitting will give us values for alpha and beta. Right now we don't know those values, and they will tell us how strong the relationship is. So if we know those values, we can put a hat on that. So alpha hat and beta hat this is a way to somehow write the fitted equation, right? And then once we know those values, alpha hat and beta hat, we can predict y hat. We can predict sales, right? By just specifying some values for X, some values for TV budget, and we can immediately know what will be the sale if I spent that much amount on TV. So it's a mathematics estimation method. The estimation of the parameters is usually achieved through least square. Well, I'm not going into detail about that. I will skip this slide. Even if you want, you can read them. It's not that difficult to read, at least. Yes, understanding is a bit complicated. So let's not go into detail about this. But one thing I would like to mention, the overall idea for those parameters is to minimize the difference between this equation. So like those guys are y hat, and if you look back in the previous slide, y was simply the equation, but when we put hat, we observed y hat. So we minimize the difference between y hat and y. And by minimizing this difference, we call them residuals, we calculate those values. So if y, the relationship, is exactly equal to the fitted value relationship, which is y hat, it means there is no error or less error. So this, considering this in mind, we calculate the values of alpha and beta. These are the mathematical formulas for calculating alpha and beta. Again, you don't need to remember those formulas because SPSS will do the job for you. Now here is a graph. So the least square fit for regression of sales onto TV. So we fit a regression line. Those dots are the values. Those green dots are the values of the data. And this line, this blue line, is the regression line, the fitted line. And we see that somehow it fits very nicely from the beginning till the end. All the values, somehow the line is in between the values. By the way, this gray line, if you notice here, those gray lines from the blue line to the dot is the deviation from this line to this point, because these green points are the data points. So we calculate the deviation as well, because of course not all the points are gathered around this blue line. Some are bit far, some are gathered like in the over here. Most of the points are gathered at the blue lines. So that's why we calculate those deviations as well, the gray line in between this plot. So we define a relationship between x and y through the following linear regression, and we know that alpha and beta are the intercept and slope, right? So here, that's how we calculate the standard error of alpha and beta, and they can help us to know whether beta is significant or not. Once we know those standard errors, we can even calculate the confidence interval for alpha and for beta. Like I wrote this equation in general for alpha and beta. By the way, this should be theta hat, not beta hat, because it's a general equation. If you want for alpha, just plug in alpha everywhere. If you want for beta, just plug in beta everywhere. So for the advertising data, the confidence interval, the 95% confidence interval for alpha is this guy, right? It means that in the absence of any advertising, because I'm talking about alpha, right? So if you come back here, if your beta is 0, it means y is equal to alpha plus error, right? So let's talk about the influence of alpha on y first. So that's what we are doing now. So we calculate the confidence interval for alpha, which is 6.130, which is the lowest limit, and 7.935, which is the upper limit. It means that in absence of any advertising, means like beta is 0, then on average, the sale will fall somewhere between 6,130 and 7,935 units. So if you do not spend anything on advertisement, even though you are getting that much units sold for your company, right? Now let's add beta. Let's see what beta will add to it. So let's say 95% confidence interval for beta, which is 0.042 and 0.053. It means for each 1000 increase in TV advertisement. Now we added some advertisement, and now we wanted to see how much this TV advertisement add to the sale, to the previous sale, which was 6,130, between 6,130 and 7,935. So now let's see what TV advertisement will add to it. So I evaluated confidence interval for beta. Now my beta is not 0, right? And it says that for each 1000 increase in TV, there will be an average increase in sale between 42 and 53 units. So 42 units to 53 units will be added to my sale if I invest $1,000 on TV advertisement, right? So, well, we see that it's not much we are gaining when we put advertising on TV, but yes, there is some improvement. We can see that. And now we can even check some hypotheses. Well, in regression, the only hypothesis we are interested in is whether we need that beta or we do not need that beta. It means if beta is 0 means that we don't need x, right? Like here, if beta is 0, then our model reduces to y equals to alpha plus epsilon. We have no x here. There is no predictor. So sometimes we do need to know, do we need predictor in our regression, or we can just avoid a predictor and just focus on alpha and epsilon. So this type of hypothesis we can test by once we got the values for beta. And here is a test statistic. Remember the hypothesis testing we talked about mean and proportions and also like difference in means. So it is exactly the same phenomena. Here we test beta against beta equal to 0, and there is a standard error attached to this beta, and we test this whole through t statistic, right? Again, same criteria. If p absolute value of p is within the region or with respect to rejection region or not, or if the larger value of p with respect to alpha, we decide are we going to reject or not reject the hypothesis. You know that. Now here, for our advertisement data, the following table provides the results for the regression of the number of units sold on TV advertisement. So for intercept, by intercept I mean alpha, and for TV I mean beta. So these are the coefficients, alpha hat and beta hat, right? Standard errors for those guys, and then t statistics and the p-value. So right now I can see that the p-value of both of those parameters is very low, actually, very much less than alpha. Alpha is standard 0.05. It means that p-value is very small, which leads us to reject the null hypothesis of beta equal to 0, and I conclude that yes, I do need beta. I do need TV advertisement for my regression because beta is not zero. I'm going to reject this hypothesis. My p-value is very low, right? And from the table, it means that for an additional 1000 spent on TV advertisement is associated with selling approximately 47.5 additional units of the product, right? So if you just multiply this number by 1000, you see that that much unit you are going to sell more when you spend on TV advertisement, when you spend $1,000 on TV advertisement, right? And just to recall, just to mention, the coefficient value for beta or for TV should or always lie within this confidence interval, should always be lying within this interval, this confidence interval. Sometimes we also need to know the overall accuracy of the model. Is the model good enough for our data or not? And we do so by calculating couple of matrices. Like, we know that we need our beta, we need TV advertisement, but is this the suitable model for us or not? So we calculated residual sum of standard errors or R square statistic. These are the guys which are very known to us, and they can help us to know whether this model is good enough for us for prediction or for assessment or not. So we calculate those guys, R square or RSSE, and then based on those values we decide are we going to use this model in future or not. So let's have those values. So for our advertisement data, the same data, and also for regression of number of units sold on TV advertisement, we calculate those guys. Like RSE is 3.26, R square is 0.612, and F statistics is 312.1, right? Now let's understand what it means. So from the table, actual sale in each market deviate from the true regression line by approximately that much unit on average, right? You see this number? So this number tells us how many data points or how many units are going to be deviated from the regression line. Now let's come back to the graph, the fitting graph over here. So you see there are some points which are deviating from the regression line. Some of them are really close to the regression line, and that's what we can see from this value. So it's like in each market, actual sale in each market deviate from the true regression line by approximately that much unit. It means that we lose too much. Our sale is not actually, or the regression line is not actually predicting somehow the accurate sale, so to say. We are deviating too much from the line. It should not be the case. Most of the data points should be attached or somehow close to that line if the regression line is good enough. But right now we see that we lose that much number of units if we rely on that regression line. So in another word, even if our model was correct and true values of coefficients were known, any prediction on sale on TV advertisement would still be off by that much number of units on average, right? And if you look at the R square value, is also not very convincing. By the way, the R square value is the coefficient of determination. Well, in a layman word, R square is the coefficient of determination. It tells us how determined we are about our regression. And the value, the range of R square goes from 0 to 100. 0 to 100%, or 0 to 1 actually, if you consider them in number. Right now, for this particular example, we see that only 61%, I have only 61% of the determination level for this particular regression. It means only 2/3 of the total variability in sales is explained by this linear regression on TV. This explains the total variability, but right now it only explains 61% of the variability. What about the rest 39%? Something is missing, and that 39% which is missing led us to go off the sale by that much number of units, 3,216 units on average, right? So we need to figure out what is missing. We need this model. Of course, we can see that R square is not very high. It should be having like 80 to 90%. Then we definitely are going to rely on this R square or on this model. But right now, R square only captures 61% of the total variability in the data explained by this linear regression, right? So it means that yes, linear regression is good, parameter is good. We do need TV advertisement for the sales, but this is not enough. This is not sufficient. We need to go beyond. So what else we can do? Well, we can go for multiple linear regression. Multiple linear regression means when we have more predictors, more covariates, like, and by the way, I attach beta 1, beta 2 up to beta p for all the covariates. So now if for this advertising example, I can have another regression with TV, radio, and a newspaper, all of them attached in one equation. And then I can see how they perform all together. Are they going to improve my regression? Are they going to improve my R square? Are they going to reduce my RSE, this value, this residual standard R? Are they going to reduce this value? Because I want less deviation. Right now the deviation is too high, right? So let's see what we get. So we fit a model with all of these three guys: TV, radio, newspaper, and alpha, the intercept. These are the coefficient values, right? Standard errors and p-values. So from the p-value, I see that, okay, I need alpha, I need TV, because TV beta is not zero. Here I reject my beta being equal to zero. Here I may reject my beta 2 for radio being equal to zero. But here I don't need, it seems like I don't need a newspaper, because newspaper for this for the newspaper beta 3 is the p-value for beta 3 is too high. So I probably do not need beta 3. But so far, let's stick to that. Here is a correlation. It says how those variables are associated among one another, right? So for a given amount of TV newspaper advertisement, spending additional 1000 on radio advertisement leads to an increase in the sale by approximately 189 units. So now if you want to somehow read those values, the individual values of each variable, just just fix the other variables, so to say. So if you want to say how much TV is going to give you when you spend on only on TV, just don't care about radio and just multiply this guy by 1000 and you will get a figure. So right now, for a given amount of TV and newspaper, I'm not thinking too much about TV and newspaper. I make them fixed. For only radio, if I spend 1000, I'm going to sell 189 units, right? Over here you can see that. And then the correlation table shows that the contribution of each media on sales, like here, TV is associated with sales 78%, 57% is with radio, 22% is from the newspaper, right? So is at least one of the predictor useful in predicting the response? Do all the predictor help to explain why, or is only a subset of predictor which is useful? How does model the data fit the model fit the data, and what are the predictors which can be used to do prediction in future for response variables? So these are the questions we can now ask. So now you understand, we had one variable, the TV sales. We run a full regression. We calculate all the guys, the p-value, the R squared, the RSE, and we assess that yes, TV is needed, but the regression is not very useful. We need more. Something is missing. 39% of the variation is missing from that regression. So then we move on further and we add all other variables into it, like newspaper and radio is now into it. And now we see that radio is important, TV is important, newspaper is not very important. But now the next question is this linear regression enough for us? Do we improve anything from previous regression to this regression, or what? So in the next part of this video, we will be discussing more about that. Thank you very much.